right now. And so kind of look at these plots not as tools for designing, but tools for QA, QC. And when you're working on a site, you want to know, are the characteristics that I'm looking at this site, how do they compare with sites that we've done before? Are they similar, or is there something unique about this site? Is the bridge that I'm proposing at this site, how does it line up with other bridges in the past? Is it similar, or is there something different here? And so these would be QC tools. They can be scoping tools that you would use when you're at the beginning of a project and you're not sure where you're going to end up. And then if you're reviewing somebody else's work, you can use them as QC tools that way. So that's the main intent of these this analysis that I'm going to be presenting. Tom and I worked together at the DOT when I was there for a few years, and we did this analysis together. Unfortunately, Tom couldn't be with us today. But Tom, appreciate what Tom did for us on this analysis. Let me back up here. I'd like to give some photographs of floods, historic floods, just to emphasize that floods are real. They do a lot of damage, and so we need to keep a strong appreciation of the significance of our work as we seek to design, in particular, bridges to withstand those events. This is a flood in North Carolina back in 1916. I believe this is the French Broad River. Again, just to show the scope of what floods can do as far as the damage here. If you want more information about the presentation, Tom and I wrote a paper presented at TRB back in 2020, and you can get a copy of that paper to get more details and background on this analysis. What I'm going to cover today is why do we want to analyze that data, which I've kind of given you a big picture just a minute ago. I want to look at the overview of the data that we used in the analysis and where it came from, and then we want to look at some of the trends of certain characteristics such as stream size, channel floodplain width, flow depths, slopes, sediment sizes, and then look at some basic bridge hydraulic design criteria such as backwater velocity and bridge length. Okay, so why I'm behind on my sorry, I'm looking at the screen over here, didn't realize what's up there. So why analyze design data? And I'm going to talk a little bit about that, and it's not responding. Okay, I'm not sure what I'm doing wrong. Anybody got any? Use this.
Well, that's not working either. Sorry.
Okay, that's all I had to say. Thank you. So just hit right. Should I just use this, the clicker?
So you can do the arrows.
I was doing the arrows, yeah.
And it froze.
Yeah. Okay. Okay. I'm in this picture. This is me 32 years ago. I don't have gray hair in that picture. I'm in the light shirt and khaki pants. And back in 1990, we had several floods come through South Carolina back to back, and the practice back then was to go out and look at the damage that these floods did. And I want to encourage you, if you work with younger hydraulic engineers, make sure that you give them the opportunity to go out in the field when a major flood comes to your state so they can see what really happens during that flood. And I'll point out, this is one of my closer friends over the years, Randy Williamson in the red shirt. He couldn't be here today, but he's with Aulick Engineer, so he and I worked together at the SCDOT many years ago. So why analyze data? A big part of it is developing engineering knowledge and judgment, which can take years and typically is gained one project, or I like to say one flood at a time. Data analysis that we're presenting today provides a supplemental tool to help you promote hydraulic engineering knowledge and judgment. It kind of gives you the big picture of the range and trend of various hydraulic variables that we typically use in a bridge hydraulic analysis. And then it can also assist you in scoping a project. If you haven't begun a project, you can look at that data and kind of get some direction about where you're headed in the final design for a new project. And then, of course, QA, QC for when you're reviewing and checking the work of others. So some of the big picture questions you might want to be asking for a given site condition. What is the relationship of backwater to flow contraction for a design bridge? Is there a relationship there? And there is. What's the typical flow velocity in your design bridges in the past, and how does your current bridge compare? What's a typical bridge length for a design bridge? And what should I anticipate the bridge I'm working on to be, or the range that it should be in? And then what are typical stream characteristics, such as stream size, stream slope, and so on at the site I'm working on, and how does it compare with other sites in that region? And is it a unique site that varies, or is it lining up well with the other sites? And so these can be very helpful, give you a helpful picture when you're working on a particular site. Okay, the two data sources that we used were USGS scour studies, and then the SCDOT has a database where they've compiled data from the previously designed bridges, and we use that. Tom and I use that data also. So let me talk briefly about those sources of data. These were the four reports from the USGS that we used as part of the analysis. There were 4 field investigations, 306 bridges, and then data includes stream characteristics, bridge hydraulics for the 100-year flood, and then keep in mind that some of these sites have missing data, so we weren't able to use all of them, but we were able to use a good bit of them. And just for information, this actually represents most of my career with the USGS. I came on board when scour was a hot item back in the early 90s, and worked on a lot of scour projects back then. With regards to the SCDOT design database, this is just your typical hydraulic data sheet for a design bridge that the SCDOT collects and stores for each bridge that they design. And we had 214 bridges. The designs were done between 1990 and 2016. And it doesn't have as much data as the USGS data set had, but the typical characteristics that we use from this data set are what are your design bridge lengths, your flow velocity, backwater, and drainage area. A little more information on the USGS sites. This is a map that shows the location of where they were located in the state of South Carolina. Again, 230 bridges shown here out of the 300 or so. The Piedmont region, and this is the coastal plain region, they have different characteristics, and we'll talk a little bit about those. This is the most important location in South Carolina where Clemson is, so go Tigers. That's where I actually live, in Clemson. The Piedmont tends to have steeper slopes, clay banks, and floodplains, more narrow valleys, and in contrast, the coastal plain tends to have flatter slopes, sandier banks and floodplains, and then much more wide, swampy type floodplains. So they're very different in their stream characteristics between these two regions. And when we look at the data, we're going to look at data from each of these regions and show the perspective of the difference between the regions. And so there's a good distribution of sites across the state, and so we think it's going to give a pretty good representation of the general trends that we see in South Carolina regarding these various characteristics. Okay, talk about stream characteristics. Basically, we're going to look at level 1 type of characteristics that you would be looking at when you're doing a hydraulic study at a bridge. This comes from HEC 20. Just the basic recommendations of looking at various characteristics of your site to evaluate its potential for stability or lack thereof. So level 1 assessment is the qualitative evaluation of a stream's lateral and vertical stability. And again, part of that assessment includes a review of stream characteristics. And these are the characteristics that we will typically look at when you're doing a level 1. And this is the data that we reviewed and compiled and looked at trends in this little study here. Okay, I'm going to look at stream size. Again, this comes straight out of HEC 20, this figure. But their stream size is defined by your channel top width. And these are the 3 basic categories: small streams, medium streams, and wide streams. And you can see the breakpoints for the widths there by which they would be classified, again, based on channel width. And this is a plot of your top width of your channel with respect to drainage area, a very nice relationship there. And again, it shows what you would expect as an increasing channel as drainage area increases. I'm going to break out this graph by channel width. You see the red line arrows on the left. But so you have small streams that are 100-foot wide or less, stream width-wise, and about 78% of the data that we had are small streams, 20% are medium, and then 2% were wide. And I suspect this is really reflecting the general trend of what you're going to see. A lot more smaller streams is where most of our work is as hydraulic engineers are going to be, and then much less in the larger streams, simply because they're not as populous. They're not as many in a given region. The small streams are by far the dominant type of stream you're going to do work with. Okay, interestingly, bridges in South Carolina or streams at these crossings, any site that had a drainage area of 100 square miles or less pretty much fit in that small stream category. So that's kind of an unusual breakpoint or a breakpoint to keep in mind, at least when you're working in South Carolina, that if you're dealing with a site that has 100 square miles or less in drainage areas, it's going to be classified more than likely as a small stream. Okay, silt, sand, and gravel, these are your various types of channel bed materials. Just briefly go through this. I'm not going to read all of these, but this is what comes out of HEC 20 is the range of the various sediment sizes by which they classify these stream characteristics. And of course, if sandy soils are going to have the largest potential for scour depth, which you're going to be more thoughtful working with those types of streams. But this is a plot of your median grain sizes for the sites that we compiled, and with respect to stream slope, there really was no strong relationship between in the data set for sediment size. We just used stream slope just to kind of filter out the data and spread it out so you could see it. But what's very notable is that the Piedmonts have a higher D50 than the coastal plain. These are the average values, and that makes sense. The Piedmont has steeper streams. They have therefore have higher capacity to carry larger sediments, and so you would expect the D50s in Piedmont streams to be a little bit higher than what you're seeing in the coastal plain. So again, if you're working in a site, you could use this graph and these average values to gain insight. Is the site I'm looking at, is it falling within the range of what the past sites are looking like? Again, basically QA/QC. Okay, this next slide is channel slope with respect to drainage area. A fairly nice relationship here. Good bit of scatter, but again, a very noticeable trend. And as your slope decreases, it decreases as drainage area increases. Again, that makes sense also. Usually your smaller streams are in the upper part of your basins where the slopes usually are steeper. But again, this gives you some perspective of where they fall out. And again, you can use it as a comparison to your site to get some idea if your site is falling within the typical range of what these other sites represent. Okay, notably Piedmont has steeper slopes, which is what is to be anticipated, and then the flatter regions of the coastal plain, they're not as steep. And again, this is just the breakpoint of 100 square miles where we know all of them are small streams, and you can see that small streams tend to have steeper slopes. Okay, this next slide is floodplain width. This is for the 100-year flood with respect to drainage area. And you can see in the Piedmont, which are the hollow circles, they're going to have more narrow floodplains, again, which is what you would expect. In the coastal plain, you have wider floodplains, again, which is the topography indicates you've got very flat streams and therefore wider floodplains. And this gives you some perspective of what that range is, and if you're working with a site that has 1,000 square miles drainage area, you can kind of go to these graphs and get a ballpark of if your site is fitting within that previously set of design bridges. Okay, again, your small bridges there, 100 square miles or less. Again, just highlighting that your small bridges tend to have not as wide floodplains. That's pretty reasonable. Okay, this is a red line makes break point between 1,000-foot wide floodplain, and just interesting. You can see by this graph here that your Piedmont streams have, most of them are less than 1,000 feet, in contrast to the coastal plain. Most of them are greater than 1,000 feet, and just kind of highlighting the difference between those physiographic regions. Okay, this next plot is the 100-year flow depth with respect to drainage area. Again, a fairly nice relationship. There is scatter, but a clear trend. And of course, depth decreases with drainage area, which makes common sense. But this can give you some idea of what that trend is. And then Piedmont streams, you can see, generally have deeper flows than those of the coastal plain. And that's primarily because they have more narrow, constricting floodplains, which is going to tend to increase your flow depths. Okay, want to quickly move on to bridge hydraulics. Show you some trends there. This is if you're an old guy like me, you actually probably have read this manual. If you're a young guy, you probably never heard of this. This is HDS-1, published in 1960 by Federal Highways, and this is what I actually started out in hydraulics, bridge hydraulics, back in the 80s when I started with the SCDOT. But this is where your channel would be. This would represent your uncontracted section upstream of your bridge, and then this would be your contracted section at your bridge. And it presents what's called the geometric contraction ratio in this book, and this is in this report. This is the equation. It's 1 minus little b over big B as defined in the graph there. And again, it's just a measure of how severe the bridge is contracting flow. And if you have zero contraction, it means you span the whole floodplain and you're not doing any contraction. And if you have a contraction ratio of 1, it means you messed up and built a dam rather than a bridge, and you need to go do something about it. So. And then anywhere in between is just a measure of the severity of the contraction that you created with that bridge. And so this is a graph of backwater versus geometric contraction ratio. And as you can see in this graph, as you constrict the flow more, eventually your backwater is going to start going up pretty quickly. So you can see here backwater versus contraction ratio. This we're based on the Westpro model, which some of you may have never heard of. But the upper bound of backwater is increasing as the contraction ratio increases, which is what you would be expecting. And again, 1 foot is a common design criteria for the 100-year flow, and you want to keep it below 1 foot. And so you can see here at a contraction ratio of 0.75 within this data set is where you start seeing a few to creep up above 1 foot of backwater. This doesn't mean you can't have a bridge, an appropriately designed bridge with that contraction ratio, but I think what it's saying is you get into that range, you just need to be more cautious and thoughtful about making sure you've crossed all your T's and dotted all your I's with regards to design so that you're not excessively contracting flow. Okay, I'm going to skip over this. This is a quote from the Missouri DOT where they found that most of their design bridges had velocities somewhere around 6 feet per second or less. And so we used that criteria, thought that was interesting, and plotted the velocities from design bridges, and this is design velocity versus drainage area. Again, not a strong relationship between those variables, but just showing that data. So as you can see, most of them are below 6 feet per second, and you have a few sites that had higher velocities. So that's probably not 6 feet per second and below is probably a reasonable target, with realizing you're going to have some sites that may have 6 feet per second or higher velocities, but not many. Okay, I'm going to go through here quickly to wrap this up. This was, to me, the most satisfying graph in the analysis, and this is bridge length versus drainage area. And so there's a very nice relationship there. And I remember as I was presenting this to the SCDOT staff, a couple of older guys kind of had a gasp, because this kind of summarizes all the analysis you do into this simple graph of, hey, drainage area, this is your bridge length on average. Now, this is not to be used as a design figure, but it's a great figure to help you gauge whether your design is falling in range of what has been designed in the past. So that was the design, the SCDOT design data. This graph includes that data, but also I pulled in the USGS data, which was just based on scour analysis. It wasn't a design study. And they fall over top of one another pretty well, just confirming that the trends are reasonable. In conclusion, the analysis of hydraulic data can provide supplemental tools, and I emphasize supplemental, these are not primary design tools, to promote hydraulic engineering knowledge and judgment. They show the big picture in hydraulic data and the trends in hydraulic data, and they assist with scoping and level one assessments in QA/QC. And again, if you're at the beginning of a project and you're wondering what is going to be my bridge length here, you can look at these graphs and begin to get some picture of what you should anticipate as being your final design criteria. And if you're reviewing the work of others, you can use these graphs to begin to discern, is this study, is it falling in line with the previous studies? So with that, I'll conclude by asking, what's hiding in your hydraulic data? So I think there's probably not any time.
Oh, we're good time for questions.
What causes the backwater? It's just like if you had a large pipe and you put a smaller pipe in, and it's going to back up your water there. So that the contraction just constricts the flow and makes it harder to pass through as efficiently. Any other questions? Okay. That's in the USGS reports I worked on. Yes, the South Carolina bridge scour envelope curves do use the contraction ratio at a bridge to assess the trend in observed field measurements of scour. So that's right, Roberto, yeah. For contraction scour? Oh, yes, and that's actually, it's in that report. So it includes graphs of that type of scour, abutment scour, contraction scour related to the severity of the contraction, yes. Yeah. Any other questions?
Any other data that you wish you could get that you just don't readily get all the time?
Oh, I love data, so if you know where to get it, let me know. So, yeah, mostly from previous studies, that can give you a lot of information. So you might want to compile and collect that data at your local DOTs. Okay, thank y'all.
Thank you, Benedict.